In this short series of videos, you will learn how to calculate the crack widths in reinforced concrete structures. The series of videos are all based on the book Structural Design from First Principles, Chapter 10, Control of Cracking in Reinforced Concrete. Calculation of crack widths in beams. The first step is to calculate the strain in the steel in the rebar, and that's carried out at working loads, and we multiply the strain in the steel by the crack spacing. And the crack spacing is derived using an empirical expression that comes from Eurocode 2 that says that the crack spacing is 3.4 times the cover plus 0.17 times the rebar diameter divided by the reinforcement ratio. You can see from this that since the rebar diameter appears here, that if we increase the rebar diameter, we will increase the crack spacing. So therefore we will increase the crack thickness or width. So if we want to control cracking, it's much better to use a larger number of small rebars than a small number of thick rebars. Figure 10.9 here shows you a cross section through a reinforced concrete beam. The beam is subjected to a working bending moment of 30 kilonewton meters. Estimate the crack width under these working loads. The first thing to do is to work out the depth to the neutral axis. We call that X. That's the distance from the top of the beam to this neutral axis position here. The best way to do that is to transform the steel into an equivalent area of concrete. And we do that using the method of transform sections. So Young's modulus for the steel is 210,000. Young's modulus for the concrete is 18,000, so we call this the modular ratio. And we multiply that by the area of steel. So this gives us an equivalent area of concrete of 7,327 millimeters squared, and that's shown by this block here. Now we're going to take moments of area about this top face here. So 200 times x, so the width 200 times x is that area, multiplied by the distance from here to the centroid of that area, which is x over 2, plus this area times that distance, which is 310 millimeters, that's the effective depth, is equal to the combined areas, so that's 200x plus 7,327 multiplied by the depth to the neutral axis. We have a quadratic equation which has these two roots. So this is the root that counts. The depth to the neutral axis is 118.5 millimeters. Now, if we take moments about the centroid of this compression block, we can work out the bending moment that is developed by this. Actually, we're already given the moment in the equation. It says that the moment is 30 kilonewton meters. So taking moments about this centroid, we can say that the force here multiplied by the lever arm is equal to the applied moment. So the force in the steel is going to be the stress in the steel times the area of steel multiplied by the lever arm, which is the effective depth, minus 1/3 of the depth to the neutral axis. So if we just rearrange this equation, we can say that the stress in the steel is 176.6 newtons per millimeter squared. And the corresponding strain in the steel is that stress divided by Young's modulus. And then we've got to apply this Eurocode formula. We need the effective reinforcement ratio. The effective reinforcement ratio is the area of tension steel, which is 628 millimeters squared, divided by the tension zone area, which is the width, which is 200 times 100 millimeters, which is 2.5 times the overall depth minus the effective depth, which comes out at 100 millimeters. So then we can work out the crack spacing, which is 193 millimeters, and the corresponding crack width is the strain that we calculated multiplied by that spacing, 0.16 millimeters. I hope you enjoyed this short video on the control of cracking in reinforced concrete. There are 6 more videos on this topic available on YouTube and also in the book Structural Design from First Principles. I hope you enjoyed this, and do press like if you found it useful. Thank you.